how to deal with those systems, like even molecules, right? Hydrogen molecule is not so complicated. Two protons with two electrons move around each other, but there's also interaction between the two atoms overhealing with the two electrons. So that even in that case, this potential is difficult. The difficulty comes from, of course, this is a single particle, right? You just consider a single particle. And here we want to like either single particle or many particle system. So in general, it is not easy to solve this one. It is a very exact and analytical solutions. So how should we do? We need resort this approximation measure. That is from this chapter 9 and chapter 10. We are going to discuss what kind of approximation we can apply to deal with the system if you have more complicated potential. So this one, perturbation, include time independent and time dependent. Or dependent. Now depend on the potential, if it depend on time or not, right? Dependent. So this will go to chapter 10, and here we go to chapter 9. That we say the stationary states, since the potential does not depend on time explicitly. And variation. Variational method. So in the variation method, most cases also deal with the time independent part. So that is chapter 9. Okay. So we are going to now you know the structure. So now from now on, we are going to deal with those the more complicated potential and how to solve the eigenvalue problem, right? The WKB method is another method to deal with time-independent case, but that is a classical limit. So to save time, I will not go through that. So basically, I'm going to discuss perturbation, variation method. These two methods. So now let's first consider time-independent perturbation sharing. Let's first still consider this a single particle. So first, we're going to consider time-independent perturbation. This perturbation is on. Okay. So what is the, in which case we can apply the time-independent perturbation theory? So if the Hamiltonian can write into the two parts. Here, the first one, H naught, can have this exact solution. So here, if F naught is this case, that the potential is simple such that we can show in chapter 4 and chapter 3 those exact solutions, then we can take. So that one is known as M perturbated. Okay, M perturbated and has exact solution. So that means H naught. Now, eigenvalue problem, right? So now I'm going to use the index not to distinguish the perturbation term and this unperturbation term. So here, energy and this the function at zeroth order over this one is energy or eigenvalue and eigenstates. Values, eigenstates. For the unperturbed. Okay. So that is if we know this. If not, of course, we cannot apply the perturbation, right? So perturbation, the zeroth order or unperturbation term, B has we know, and we have the exact solution. Then this one, because the perturbation term is known as perturbation term. Okay, and this one, and here, such that, so when they say perturbation, that means we have this condition. So the exact term is much, much larger than the perturbation. Then we can say that the perturbation term is just the correction in respect to, based on this exact term. Right? So that is condition if this is satisfied. Okay. Then we can apply this perturbation term theory here. So once we have this, now how to apply this theory, right? The theory is okay. So how to apply, right? The perturbation theory. Let's do first. Assume or define. Let's define. The perturbation term can be written in term of lambda and the operator the W. So this one, you may say, how can I introduce this one if I know this one? This is just intermediate step. In real calculation, we don't need this one. You just need to come to here. But we are going to analyze the perturbation in zeroth order, first order, second order. So we're going to introduce this just lambda is it is a parameter. It's just a parameter, which is very, very small, and we are going to use this as intermediate step, just a temporary parameter. Then we are going to apply this form to go to this eigenvalue problem and solve that by different order, right? So that is, don't worry this one, we just introduce this. So then, the eigenvalue problem, right? Eigenvalue problem over time and children equation is H here. We are going to solve this, right? So this reduce to H naught plus lambda W, and then here this side, this is we are going to obtain this eigenstate correspond to the eigenvalue. Okay. So here, any nth order of energy speed start from this initial zeroth order, this perturbation term plus the perturbation, right? Perturbation contribution. And similarly, the corresponding eigenstates should be also the eigenstates as the perturbation term plus the contribution from this. So that is the basic idea. Right? The basic idea is that if this perturbation Hamiltonian much, much smaller than the perturbation term, so we can apply this. How to apply? If we introduce lambda, so the perturbation term, since lambda is smaller than 1, so this is a smaller term. And then this eigenvalue problem is reduced to, so this, I just replace Hamiltonian by H naught plus this term, right? Then correspond to solve this, the result is the energy for this with perturbation terms be and perturbation term plus the contributed from there. And the eigenstates also this. So now the remaining part is how to obtain this, right? This is what we are going to do. Now to do this depend, right? So this depend the solution, okay. Solutions, it really depends. Depends. Solution depends. On what? Whether it is degenerate or undegenerate. So degenerate and undegenerate is a different way. So we are going to the degeneracy of a perturbation energy. That means depend on this the symmetry or the behavior of this. Then we are going to discuss the two ways. If it's non-degenerate, how to make the correction and find the perturbation term. If degenerate, what is the determine this contribution from the perturbation. So now we are going to discuss one by one. First, now non-degenerate perturbation. Okay. Okay. Non-degenerate means the states and perturbation states and energy will correspond one by one, right? For one different states, or for one, it's only correspond to one energy. If I change another state, then another energy. Okay. So with this, now how to do that? So, okay, so now we are going to use the Taylor, apply the Taylor expansion. In terms lambda, since we know this is a perturbation term, lambda is very small, right? So in terms of lambda. So the energy here, right? So nth corresponds to the nth level, the energy with the perturbation. So the zeroth order is the perturbation term, plus the first order, I'm going to use En1 with lambda first order, and then in terms of this lambda is Taylor expansion, right? Type of, sum of like Taylor expansion and height. And similar states is also expand in terms lambda. So I introduce the goal, or the next step is try to find En1, Psi1, En2, Psi2. That is M means for gate, but correspond to correction on this level, right? So I have index here. And those indexes correspond to here. We already have this one. So we have energy spectrum for an perturbative term. Like here we have a perturbative term, En0. And now we are going to switch on this perturbation term. So you see the energy may be modified, right? So that is, the idea is consider each one, okay? So once we use this one, we need keep in mind here. First, it is, in most cases, we can write in this way, but it does not mean always. Sometimes we cannot write. So that is node. Let's say such expansion holds in most cases, but we cannot say in every case we can expand. So that just keep in mind in most cases. Second one, in term lambda might not all are converged, right? Might not always converge. If not convergent, so that means if you make the high order term, maybe there are some terms we cannot ignore. But if we consider the lambda, if we can write in terms, but if lambda, we select lambda is much, much small, right? In most cases, the first and the second order is enough. Are enough. So that is basically, we just keep in mind when we apply this perturbation theory. It is, ideally, yes, it is. But in practical, we have to keep in mind whether we can apply, right? So that is just keep in mind we apply by this condition. If the perturbation term can written in this way and with very small parameter, then we can do. Okay. So with keeping this in mind, now we introduce En and psi n in terms of this we are going to substitute into here. Right? So okay, Hamiltonian, okay, so now here we have a Hamiltonian. And the states, right? Psi n now. Let me first write down here. And then substitute this two expansion into this eigenvalue problem. If they come here, H naught, this the operator Hamiltonian, they keep it here. But now this inside, there's order lambda, first order plus second order plus. This is the left hand side. And the right hand side, anything is zeroth order, first order, second order, and the states, right? Okay. So what we need to do is we are going to seek this equation, the left hand side in terms of lambda. So for same order of lambda, the coefficients be same, right? It's be equal. So now from here we are going to see the zeroth order, first order, and second order, right? So now in terms of lambda, right? So now zeroth order is this one, right? H naught multiplied this one. We have lambda, so there's only this term, left hand side, right? So zeroth order is which one? Left hand side is H naught, side N naught. And the right hand side is only this one to this one, right? The others has lambda. And this is nothing but a perturbation Hamiltonian is the eigenvalue problem for the perturbate, right? So this one, the exact solution we know. That is zeroth order, and that makes sense since no perturbation. Now, first order, right? First order, let's look at the left hand side. So this one, this. We have this, and we have also this one, right? So we have two terms, H naught. Okay, here, right? H naught multiplied this one. Second one. Last, this, so that is W. No. That is left hand side. Right hand side. Right hand side, this one here, right? This is lambda. So that is En naught multiplied with psi N1. And then here, this one, En1 is sign out, right? Yes. Right, that's all. And the others be highest. So now let's go to second order. And you do the same thing for the higher order. So now let's up to the second order. Second order is this one to this one, right? So that is left hand side H naught, side N2, mass H naught, this one and this one, right? So this is a square. This is square two times, yes. So W side W side in one, right? That is the left hand side. And the right hand side, here, this one multiply this, and this one multiply this, and this one multiply this. 3 terms, right? So let's do that. E naught, En naught, multiply this. It is very easy that you can see that the superscript, right? If this is 0 and this is 2, this is a 1, this is 1, so that is 2, right? We just this thing, so that 2, and here En1. En1 is 1, right? 1, 1, 1. And En2, 0, right? Okay, so the others, right? Higher order term, you do the same thing. Just compare both left hand side, right hand side, correspond to in term lambda order, and then you can set up each different equations. All right, let's say that. So now, this one we already have. So now the next ones we are going to find this energy and this, right? So that is first order. The second order is we are going to find second order correction energy and the second order the wave function. So before we doing that, we're going to apply some property here. So orthogonal, right? So there is a normal normality of this eigenstate. That's because we know any state inner product itself or known of itself to be equal to 1, right? If normalized. This is we are going to solve. But whatever it is, a states, eigenstates of the with Hamilton with the perturbation term, but the inner product itself be equal to 1. So now let's see here. Psi n is this one, right? So now you can see the left hand side, the right hand side actually is equal to. So that means, let me do that. Is, let me first suppose this one, so is explained as 0th order with the cat plus the first order with the cat psi n and lambda square second order psi n and equal to here. Then I'm going to, for each term, I'm going to extend this cat. Right? First, substitute the Taylor expansion for broad. Then each term, there's a cat. So we are going to do that. So you will see this is a 0th order inner product and lambda first order and lambda square log, right? All the other term. Okay. So because that's this one is normalized, right? This is an unperturbation term, so that's B1 plus lambda plus other term. All the remaining with lambda, right? So that means all the speed go to 0, right? Because this equal to 1. The left-hand side is 1. Right-hand side 1 plus something. And that speed, all speed 0 to make it normalized. So we have the conclusion. Any inner product of this higher order, I'm going to use a K, with zeroth order, speed always 0. Here, K is 1, 2. And of course here, that is for same n. So that is the property we are going to apply, very important. Okay, now with this property, now we are going to solve the first order to obtain the energy correction from first order as well as the eigenstate. Then we go to second order, right? So now we are going to go to solve this one first. This one is we are going to deal with this one, right? So this one is the eigenvalue problem for first order, and then we are going to, unknown part is, which we are going to solve, is here and here, right? So let's see how to do that. Okay. So now let's consider solve the first order. We are going to find this and this. That is our goal. From where? From the equation h naught set n plus w, right? Equal to E naught set n1 plus E n1 set n naught. Okay, this is the equation we are going to solve. Now, how to solve this? Those techniques we already learned in our class from last fall. So now, think about if I want to obtain this one. So that means I'm going to take the inner products or multiply the graph. So that is a matrix element, and then here is a constant. So we'll give inner either equal to sum of number or equal to 0 by apply this, right? So what we are going to do is, the goal is find this, so we are going to apply two things. First, we know for the zeroth order, this gives us, and then this so normality. So we are going to use this now first. So now let's first find this one. How to do that is multiply. Okay. Wow. The reason why is because here we are going to find this one. So if I multiply the same thing here, this is normalized, right? So I can get this one. And then the remaining term we are going to see. So now, for this, to obtain this one, I just multiply the graph from the left-hand side, both sides, right? So then we have graph, sin naught, h naught. This apply this equation, right? Like 1. And plus graph second naught plus n naught and w slash n. So that is the right hand side. And equal to right hand side. Since these are numbers, right? So I'm going to keep here number. And this is graph n naught. And cat 1, n1. And second one is en1 graph n naught. And cat also graph n naught. So we have this. the reason why we want to obtain it, so we use this multiplied bra. Now, this one, as I say here, right? The Hamiltonian is a Hermitian. So applied to the bra, it gives us energy, right? So then so that is E n naught. Right, first one. Second one to keep here, right? So not that keep here, which we need to calculate. That is the matrix element of this perturbation operator between the states, same states, right? These states we know because this is zero and perturbation term. That is left-hand side. So right-hand side here. Okay, and not this one. Here, right? 0. Second one is E1, and this is 1, right? Because number 9. So now you can see right-hand side this one and the left-hand side here. This is also 0, right? Because this is 0, this is 1, right? So very easily we can obtain the first order energy eigenvalue correction is nothing but this inner product or the matrix element. Very easily is the matrix element of the perturbation term between this perturbation eigenstates. Okay. But you say, this is a W, but what we know is HP, right? So now, then come back to see the energy. If we just correct up to the first order, so energy is perturbation term plus this one, right? We have lambda. So now, the perturbation term and lambda with this, right? Multiply here. And this one is lambda multiplied W is HP, right? So this sometimes we also call EP to the first order. And keep in mind this one is correspond to the N, right? So now this is what we are going to find. And now this, so that means you see, even though we introduce lambda, we do not need it, right? We just need this. So very easily you can see the energy correction if we satisfy the perturbation up to the first order is find this perturbation Hamiltonian, do this matrix element between the n states of perturbation states. And that is. So we answer this question first, right? Now we're going to see how to obtain the correction on the states, right? How to obtain this one. Okay, so now the question is how to obtain this one. How to do that? I do not know. And now, what we are going to do is here, as I say, if this is unknown, but we are going to find the relation between unknown and known, then we are going to find that relation. That what does mean here? I remove this question here. That's why I always insert this identity operator, because this equal, right, equivalent. And I is summation of all these eigenstates. So since we have this information for the exact, so I'm going to say again, zeroth order, right, that was I, right, and cat. So this is a very important tool is that since this is equivalent, but this one is equal to this. So the goal is, since this is we know, then we are going to find, the goal is now try to find the inner product of this. The unknown one project to the known. Right? So that means we are going to find this. Oh, sorry, this is there. right? So now this goal is find this. Now first, before we do that, we are going to apply this one. If m equal to n, so that's 0, right? So here summation for all n. So when m equal to n is 0, right? So only the term is m not equal to n. Now I'm going to move this. This is numbers, right? n. Now you may say, I do not know this one. Yes. How to do that? We again use this equation by multiply the bra, because this is a inner product bra. So which bra you are going to use is n, is this term, right? Here we use n because we are going to find this one. So that we multiply the bra set n naught. But now we are going to obtain for bra m naught, the inner product is set n and the cat, right? n1. So I'm going to multiply the bra m naught, right? So that is the difference. Okay. So now for this one, we're going to on this equation here. Okay, so now the left-hand side is h naught sine 1 naught. Well, we have no number, right? So and the right-hand side is e naught sine n, which is we are going to find. It's here, right? This is what we are going to do. And en1 here, as I said, for m not equal to n, right? Because m equal to n is 0, so we don't need that. We don't need this. We just found. Then here, this one, we know that is e m naught sine n naught sine n1. And here I still keep right here. This one is non-zero because n equal not equal to m. If m equal to n, that's 0, right? So I keep here. How about this? These are all zeros order. So that is 0, right? This is 0, so no term. Okay.
What's the difference between that 0th order?
Okay. This is a result perturbation. This already we solved.
Right.
And assume all are satisfied and orthogonal.
Yeah.
So that is 0.
Okay.
Right? And this one, we don't know this one, but we prove that if normalized of this, we prove this one, right?
Yeah.
So when we prove this one, we only have if m equal to n, but all the other order also 0, right? But here m not equal to n, so we not 0.
Okay.
Okay. This one only for this.
Right.
Only for this, right? But this is not, so not be careful. Here now we have this one and this one. They are same, right? And which is we are going to put. So I'm going to move this one, this to the left hand side of. Okay. Let's see which one. Yeah, go to the left hand side. Then we take. Okay. So here. You have moved to that side. I have E n naught minus E n naught in the denominator. If I move this to the left hand side, so then I divide by this both sides, so I have this one equal to so this coefficient is simply this again we make the element of this perturbation term between the two perturbation states, but now state is different, and divided by the energy difference. Okay, now let's summarize. So here, if we only correct these states, or eigenstate up to the first order, so we have a zeroth order plus lambda, first order, and now zeroth order to here, lambda, and this one is here, right? Summation for m not equal to n. And then this one also here, E n naught minus E n naught, sin n naught, U sin n naught. Just replace this one to here. Okay. Now, if I move the lambda inside here, that is nothing but HP, right? So finally, that means the correction to the first, up to the first order is zeroth order, which you have already US solution plus this the first order, which is this term. E n naught minus E m naught in the denominator, and since m not equal to n, so this is not zero, right? Non-zero term. And then here, the inner product is the inner product of HP between the two perturbation eigenstates. This is the coefficient, and this coefficient is correspond to this one. All right, so okay, let's also go to that. I just removed that. Now let's consider the second. The first one, we have formula for energy for states. Now if we consider up to the second order, so we're going to find energy correction up to the second order and eigenstate up to the second order. So from, now I'm going to remove this left-hand side 6, right? This is the second order. This is the first order. And then here, this is second order. This is the first order. And plus. And use this space here. Plus and second order. Right, that is the second order equation. Remember, I erased over here. So now, again, we are going to use those. And then first things, let's consider energy first. In case first, so now how to do that, because we want to obtain this one. So we are going to apply the multiplied bra psi n naught, then here this is 1, right? Normalized, that is this one, the remaining term is 2. So nothing is n to this. Now the left hand side is this. So now here is 2, right? This one. And this one is 1. Right, that's the left hand side. And the right hand side, here, the first one, this is a 2. Second one, this one is 1, right? And plus third one. And this one is 1, right? Okay. Now, this one, this time. So this one, we know that is E n naught psi n naught psi n2, right? And 3, 0, because this is orthogonal. And the second one, they keep it. And this one, we're going to use this here. Yeah. This one. Right? The coefficient here, right? So that is. Let's keep it here. Here, that is left hand side. And the right hand side here, this one is 0, because this Those are all n, right? So n to the zeroth order and second to this 0. This one not 0, right? Because it's 1. This one also 0. Yeah. Yes, I know. So this is only the this one is 0, right? Okay, so let me summarize. Here. This is 2, this is 1. So then, okay, let me just substitute here. 1 you already obtained, right? So now here, that is lambda just do this, that's it. Keep adding that. So here, right, n now. Now this one is summation, right? M not equal to n, en not psi m psi a, this is n, right? Yeah. So now, then let's keep, because you see this is the inner product between this one and this, right? So you see this is a n and say n not m not, say m not, so that is square. So that is m not equal to n. This is the second order energy correction. Then this, so now that is En2. So totally, if energy up to correct up to second order, so that is this formula, right? And the first one is zeros, and perturbation term. Second one is we know that is the product or the matrix element of this perturbation term between the zeroth order eigenstates. Now here, this one. Now I have a lambda square. Multiply here, lambda square is h square, right? So that is very easily. So now this is h. Principle we can write on this way, plus EP first order and plus EP second order. But EP first order is this one, it's not the W term, right? And the EP second order is the unit product or matrix element of HP between these two states. So what we have is you're going to find this instead of En1 and En2, but En2. this is for EP1 and EP2. And that means you have the perturbation term, so you just do this. Okay. Now we go to this textbook we didn't discuss, so I'm going to discuss here. Follow the same thing which we did for the first order. How about the United States the contribution from second order? We can do the same thing. We use this. I'm going to insert I right here again. In this way, since in this way I can project the unknown cat to the known basis vector. So that is summation m. So now we use to find this, right? And again, since we have this when n equal to m equal to n, so that's 0. So then again that is only m not equal to n, right? Only found is in the product of the second order to the 0th order is m not equal to n. Then for this, again we are going to multiply the graph psi m naught to this equation. Okay. Did I apply this graph? Okay. That is yeah. All right. So now left hand side. So m naught h naught psi. That is 2, right? 2 mass psi m naught w psi m1. Left hand side. Right hand side, we have that e n naught, and this psi m naught psi m2 plus e n1 psi m naught psi m1 plus e n2 psi m naught psi m0. So this one is 0. And this one we know. This one we are going to take, right? Okay, this one. So this one is E m naught, right? Psi m naught, psi m2 plus this one again. Equal to here we also need equal to 2 terms, right? So E n naught, which is this, plus E n1. Here this is non-zero because this m not equal to n. But we know this. First order we obtain this in the product. So now what we need to do is this are same. So I move this to the left hand side. I move to the right hand side. So when is the inner product of this one, which we are going to prove over 10, is equal to the denominator is E n naught times E n naught. Right? And then here we have 2 terms here, right? First one is psi m naught w psi m1. Another term is one. Okay, so we have this formula. Now, since we also already know En1 and psi n1, so we just substitute that into this formula. You can see it became more terms, but it's still doable to find the variables. The first one we need, I think I already did the sum here, right? So we need to do this. So then we do the first term. And that is set m, no, w, right? And set n, set n1. So that set n1 is summation m. Now I have another m, so I'm going to use m prime. M prime not equal to n, right? It's this one. This one is, if you remember, so I have a bit of attention. Let's remember that. So that is m prime. Okay, now just divide it as first. So this one, right? So this one is this term. Is this part is one. So this is psi n1, right? This is a coefficient and that. Right? Now second term. Second term en1. Let's just keep en1. So we know that en1 is right? So I just keep because it's if you want to write calculated is also fine. That is this is here, this one, the only difference is this is the inner product between m and m prime on this one. This one is, okay, that is numbers. So here, if you put it here, then you have, okay, that is this. Let's keep the first term, let's go to here. And I put inside, so that is the summation n prime not equal to n. Then here, this is n, so then we have, let's do this one first. Psi n prime, psi n, and here this is a psi n, psi n prime, right? This one. So that is here. Then your summation for n prime, that is 1. We cannot, because this is yeah, let's keep here. And second one here, you see this is m and this is m prime, so this is orthogonal. Only m prime equal to n, right? So this summation when only m prime to n. So that is why the second term is really simple. We have no summation now, so that is psi m. So here, m prime, because I have this inner product is this one, this old, zeroth order, so they are orthogonal. And for the summation for old m prime, only when m equal to m prime, non-zero. So this term, this summation disappears at m prime becomes square. Okay, so that is the formula for this coefficient here. Then we can make a final this is the final expression of this second order. So the second order is summation of n and n not equal to n, and not equal to here. This is here, right? So equal to summation m not equal to n. And inside the first one, we have another summation. First one is n prime not equal to n. And here, e n naught minus e n naught. I think somewhere, I think here I have a denominator, right? That is here. E n naught minus e n prime naught. That is calculated back. So here. So here we have a two product of the two with the difference in the denominator. Then the numerator here is this two, right? Like this. And then first. And another term. Another term is this one. E and y. M. I think I also miss here, right? Miss another determinant. But when we have psi 1, we have this term, so that I also miss here. This one. And this term is two terms. So here there's also e and 0 minus e n. So this is square. E n naught minus e n naught square. And then finally this one. Okay, that is a general formula. So now we are going to apply to discuss example. So now here, this validity to see this, to use this one is the validity we need to check because we have denominator here. The validity is that this term, we want to have this term is a contribution from the perturbation term, compare with the energy difference between these two states is smaller than 1. And this contribution compared to this one is much smaller. That is the condition or validity to apply this perturbation term theory. So if this does not hold true, we cannot apply, right? Now, if we have time, let's do example, see how to apply. Consider we have a charge Q with mass n in 1D harmonic oscillator. Harmonic oscillator. And then subject to this electric field, put into the subject to a weak. When I say weak, because otherwise it's strong, we cannot use perturbation, right? A weak electric field. Epsilon in x direction. So that is a problem. And then ask her to find first the exact solution. Of such system. And calculate energy up to now. First now here. Up to first. Now zero track. Now zero correction. Okay. So let's see how can we do this. First, we write down the Hamiltonian to analyze which one's perturbation term and are they satisfy the perturbation. So, solution. Because in Hamiltonian, H naught, right? You know H naught without perturbation, and that is a one-dimension. Harmonic oscillator. We already know that one dimension has a kinetic energy for m e square to x square, right? Flat potential. Let's use this omega. So that is H naught, right? And the chapter 4 we will obtain this. That is a perturbation, electric field. So electric, when you have a charge Q in the electric field, that is this, right? The charge inhibits the electric field, and then around the x direction. Okay. So since epsilon, epsilon is small, right? Is small. So that means this is weak, right? If this is small, this is weak. So now let's consider this firstly for A. And for A, which is the exact solution. How to do the exact solution? This one is even we do not apply this perturbation term, we still can solve this one. Okay, let's look at photo-Hamiltonian. Photo-Hamiltonian is H naught plus HP. And H naught here, kinetic energy term plus potential. Now also plus perturbation. So we have a square, we have a first order in terms of x. Then we can replace by y such that we can, so if we define y is x plus a constant so y square is x square plus 2q epsilon m omega square x, right, plus square q epsilon then here you can see I have this curve. I have this curve. The only difference is the coefficient, right? So now we can make the coefficient. So then so because if we define this, now we can rewrite the Hamiltonian. You will see what is nothing but as the harmonic oscillator is a constant. Like you have this string here, you have a mass here, right? And if you just that's initial, so you vibrate, and then if you this initial, this sum of a constant to somewhere at initial, then you will find the vibration with another shift distance, right? Something like this. So now let's do this. Then you substitute, you can see the Hamiltonian is plus half of m over the square. So now I'm going to, x squared is just y squared minus those squared, right? So now it is y squared minus 2q epsilon m over the square. Yeah, x minus q epsilon m over the square, right? And the plus q epsilon x. So now, oh, sorry, here. If I define dy, y and dy is dx, right? So then here I can immediately replace by dy, right? So that is a d squared, right? Okay. Now here plus half of m over the square y square. And this term, you see m cancelled, omega square cancelled half, so that's minus q epsilon x. And here plus, so cancel, right? And then the remaining part is this one, minus half, okay. So you can see here, this is just square, so we have m over the square, right? And q square over the square. So this term is not cancelled. Then you can see this rewrite in terms of y, which is a harmonic oscillator with a variable y. And y is nothing but x plus a constant. So the solution is the same, since we know the solution is difference only on the energy and advanced constant, but the wave function is the same, right? Minus c. Okay, c is this constant. So now we're going to solve this. Now if I solve this one, I can write this one as substitute the Hamiltonian. So here I have a Hamiltonian. Plus half of m over the square y square. I move this to the left hand side, right hand side. So that is E plus C. Do you agree? I just because y I have this constant, right? So when I'm substituting the left hand side, so but this constant I just moved right. So this is a which is then this one you have a result. So very easily you can have E prime n is the n plus half s bar omega, right? This result we already text, I just okay. And then that means E n En should be this term, shift the C, right? So that En is En prime minus C, right? And that is N plus half of S bar omega minus this term, constant. Okay, N from 0, 1, 2. So we obtain exact solution. Okay, and then we are going to apply the perturbation term to obtain the contribution from here. Then you will see you got the same solution with this. And this way is try to double check this perturbation how good it is. Okay, we keep continuing on Wednesday. Since we do not have time, you have another class. Okay, let's stop here. And remind you that Wednesday, the Formula 4 is still, if you can finish, page 10.
I always worry you can't see, or that I'm in the way.
I can I can always see.
You be careful this chair. I know this chair is not strong enough sometimes. Yeah, because we have some of the chair in our lab, and the student suddenly broken up. So be careful. Okay, all right. This is you're all familiar with, right? You have learned before the perturbation. Good. So maybe I can speed up. Yes.
Wednesday,
I'm sure he left the grade, but
I
she's
may
usually.
have my niece and nephew because it's their spring break. If I have them, is it an issue if they're here in class?
Plus, I will keep continue these classes.
Yeah,
And they will be general.
okay. But if I brought them, would
Yeah.
that be okay?
I think that's be okay.
Okay.
Those are not like
Oh,
since you learned
yeah,
before,
so
and not like in
Yeah,
the
then-
chapter 8, the concept.
I haven't done perturbation.
I'll do it with you.
So this is
I
different.
can
Oh, okay. Yeah, let me summarize my slides
Okay.
later and post on that one.
I was the only person in my quantum class, my class of one, so
Yeah, yeah,
it
yeah,
was
yeah.
like
Okay.
meeting in the
Sure.
professor's office in undergrad,
Uh-huh,
and so,
Okay.
yeah.
all right. Okay, just let me know.
Okay, I mean, I plan on being here,